In this upcoming session, we are going to introduce Andrew Feldman, the CEO and co-founder of Cerebras. Andrew is going to give us a 10 minutes presentation to tell us more about this newly released AI inference chip. And after that, we are going to invite the general partner, Steve Vassallo from Foundation Capital, to have a fireside chat with Andrew. Let's welcome Andrew.
Good morning. Thank you for having me. For the last 4 years, I've been trying to explain to my parents what I do for a living. And like many of you, I'm sure you know this is not easy, and that my first effort, that concave optimization over very large state spaces, did not illuminate. Right? That was not the right approach. What I do is I build a new type of computer. Type of computer optimized for what we believe is the most important workload of our generation. A workload that is proliferating across industries and across applications. A workload that grew between 2012 and 2018 by 300,000x. All right, that's 25,000 times faster than Moore's Law when Moore's Law held. And so this is what I try and explain to my parents. And the other day, I got a text from my mother with this. It's a poster at a bus stop in Palo Alto. Yeah, I see you all have mothers. And my mother's note said, "Is this what you do?" And I try and be a good son. I said, yes. And shortly after, I get a text from my father, and it just says, "Third graders, question mark?" To which I answered the only thing possible. I said, "Adults are welcome." Right. We started our company 4 years ago to solve a very specific problem. The problem that it takes too long to train models. And we couldn't have articulated this better than Greg Diamos from Baidu did when he wrote in a recent publication, training large models on large data sets would take months or years of critical path compute time, making these training runs impractical for any real-world problem. This is the problem we set out to solve. In order to solve the problem of training, one must first understand what is happening when one trains a model. And it turns out, at the 50,000-foot level, it is very simple. Training is a feedback loop. And training time depends on the rate at which inputs move through that loop. Interestingly, it's just that simple. So, what happens inside that loop? Only two things: calculation and communication. So to accelerate training time, to reduce the amount of time it takes, you must accelerate calculation and you must accelerate communication. How do you do that? Well, what does calculation? Cores do. Actually, Fmax inside of cores, but for the first reasonable approximation, cores do. So you got to add cores. And then what do you have to do? You got to make sure that these cores that you added are utilized all the time. All right, that they're not idle. And the way you do that is to put memory right next to them so they're never waiting. So you put huge amounts of on-chip memory very close to cores. And the final thing you do is you connect these cores with a fabric that allows the cores to work together to solve problems that would take an individual core a very long time. That is what you do. Now, all of these suggest you ought to build bigger chips. And they didn't just suggest it to us, they suggested it to NVIDIA. And between 2013 and 2019 today, their chip size grew by just under 50%. Why? They were trying to get more cores and more memory and more communication bandwidth packed onto a single piece of silicon. We think that's the right approach. only we think you ought to go bigger. So this is my co-founder, Sean, MIT alum, both undergraduate and master's. We announced the largest piece of silicon ever made. It's 46,225 square millimeters of silicon. It's 1.2 trillion transistors. It's 400,000 cores, a huge amount of on-chip memory, vast amounts of memory bandwidth, and a huge fabric. Photos, welcome, keep going. For you, I make special deal. We yield 100%. Right. That's right. So that's a great question. By yielding 100%, in comparison to NVIDIA, our silicon cost is a third. They're yielding a third at 815 square millimeters. Pretty cool. Because my whole life I've waited to have something I could market so clearly. I've got show and tell too on stage. I'm going to show you one. In real life, it's just a hair smaller than this. You guys don't have an intuition of 46,000 square millimeters? Come on. By way of comparison, right, we're 56 times larger. We have 78 times more cores. We have 3,000 times more on-chip memory. We have 10,000 times more memory bandwidth and 33,000 times more fabric bandwidth. We're not messing around. We boiled performance gains down to something very simple. More cores, more memory close to cores, more low latency bandwidth between cores. You don't have to understand a huge amount about computer architecture or 100 other things. Those simple elements drive performance to the first order. Somebody down here yelped up about yield. Turns out that was a hard problem to solve. So was cross-die connectivity, super reticle connectivity. But there were many other hard problems, and it was a little bit like, for the 70-year history of our industry, nobody made a chip this big. It's like at the beginning, the guys who got halfway up Everest came back down and said it's really hard that first half. When the guys got all the way up, they came down and they turned to the guys who only got halfway up and said, no, the first half isn't that hard. It gets harder. The problems of thermal expansion and CTE mismatch between a very large chip and the underlying printed circuit board, the problem of packaging and assembling, and the problem that when you build a chip that's 55 or 56 times larger than anything else ever made, there is no manufacturing equipment available for your part. We had to invent all of it. There were no SMT machines. There was no ability to handle, place, test something this large. And if that wasn't enough, the bane of all hardware guys' existence, as you know, is what? Software guys. That's right. That's exactly right. I see some hard, these are my people here. This is great. I got to hang out with MIT people more often. Maybe I made a mistake going to Stanford. You then had to make it easy to use. And you had to make it so easy to use that it required no changes to their existing models in TensorFlow or PyTorch. Somebody's got a cool little jam going over here. Is this? Look, before we dive into some Q&A, we build big chips because for this workload, they process more data, producing answers more quickly. It's not true for all work. It's true for this work. And what that allows us to do is to deliver the performance of an entire cluster. Often one of our systems can deliver the performance of 0.5 megawatt of competitors' performance. Put lots of memory close by. Build on-chip interconnects. Don't force the ML community to bend their ideas to your hardware. Allow them to play with their ideas. Are their ideas extremely sparse? All right, those break wide vector SIMD machines like GPUs. All right, create a compute landscape that doesn't just allow us to accelerate Hinton's ideas and Bengio's ideas from the late 80s. We need new ideas. And that's what we built this system for. Everybody know what this is? Come on, zero. I finally find an audience with enough gray hair to make me happy. And now my one slide for young people goes over there. Okay. This is Dota. Dota is a team-based multiplayer game. And the guys at OpenAI are the world champions at it. And they built an artificial intelligence to play. And they trained it over 45,000 years of human gameplay experience. It was about 180 years a day, and they trained it for a little over 200 days of gameplay experience. Now, what happened 45,000 years ago? No, this is 5,000 years ago. Right? We hadn't domesticated animals 45,000 years ago. That was 10,000 years ago. In fact, we hadn't invented farming. That was 23,000 years ago. Now, what we want to do is enable them to go 100 times faster. So that would enable them to deliver 45,000 years of gameplay experience in 2 days. Or over 211 days, 4.5 million years of gameplay experience. 4.5 million years ago, we separated from apes. By way of wrapping up, it is our belief at Cerebras Systems that the largest problems of today are the smallest problems of the future. And for that, I want to show you this. This is a robot, self-driving robot called Princess Robot. It was designed by a kindergarten class in Cupertino. It was their science project. All right, so I'm not building machines for third graders. I'm building them for kindergartners. And it's for her we're building this new world. All right, that's who we're building equipment for. Steve, you want to come up and we'll do some Q&A?
All right. Thanks, Andrew. That was awesome, as always. Now you know why we invested, right? Maybe I'll start, Andrew, by asking, what were those goats on that second to last slide?
So these are North African tree climbing goats. They learned to climb trees. And there's very little vegetation, and so they evolved to climb trees and nibble at the greens on trees in Morocco. And I didn't really have a better slide for the domestication of animals. Certainly not one that related to learning.
Yes. I'm sort of the connection maybe to iterative algorithms being fascinating in that they can lead to these artifacts that you could have never predicted from their antecedents, right?
That's
maybe that connection as well. So Andrew, I'd love, maybe we could go into the Wayback Machine. You've been working on this company for 4 years, but you've been in the startup ecosystem for 25 years now, longer maybe. This is your 4th startup. And when you started Cerebras, what were at that time the greatest challenges that you saw to get this going? And how does that compare to kind of where you are today? You had some of the technical challenges, but I'd love for you to kind of unpack, you know, how that's, what it looked like then and how that's evolved over time.
Sure. First, just, it's my 5th startup. all previous 4 were successful. But for the venture capitalists, 4 to 5 is close. It's good, right, Steve? The problems we saw at the beginning were how we were going to accumulate talent. We are system builders. We're not just, we don't want to sell chips. We want to bring to ourselves a huge technical challenge, because it's our belief that the most dangerous place for a startup to end up is a little bit better than the competition. I want engineering risk, because NVIDIA can cut price. They have all the share. They can bundle. They can do 100 things if you're 1.5 or 2 or 3 times better to come at you. If you're 100 times better, there's nothing that can be done. So we had a strategy. We'd studied the history of successful hardware companies. We had big lists of things we'd done wrong in the past. We knew that this effort to build a company that did radical innovation at the processor, in physical design, in power delivery, and in cooling, in software, had built a compiler and in algorithms. This was going to be an enormous effort. And what usually limits us is the scope of our professional networks. And especially when you're growing fast. And so we were concerned at the beginning that our relationships didn't extend to world-class computational scientists. That we didn't know enough ML algorithm writers. We knew large numbers of world-class chip designers, DV guys, physical design. We knew world-class compiler guys. We knew guys who could do place and route, who in the past did EDA tools. We knew all this, but that wasn't enough. And so that worried us a lot, and we worked really hard to attack our weaknesses. We are believers. All the founders worked with me at our last company. And Gary Lauterbach, our CTO, was my co-founder at the last company.
Gary's an interesting chap, by the way. So Andrew, I sort of joke about this from time to time. I love to invest in missionary misfits, people who kind of don't fit in easy buckets. Maybe some of you are those kinds of people. And Gary is just this crazy guy who literally holds the world record for bouncing radio waves off the moon.
If any of you are ham radio guys and do moon bounce, there you go. Right, you know Gary.
Mort, right on.
Gary, right. So after 16 hours of doing work, digital design, Gary goes home and does RF as a hobby, right? And our relationship is really good. Gary remembers 50 of the patents that he owns, and I've made 0. And so we have a perfect understanding of who's responsible for what in the organization. That's worked really well for us for the past 13 years. And so I think for us, part of, just like architecture, one of the most important steps in computer architecture is being very clear about what you don't do, right? What you're not going to be good at. Because once you start saying, I'm not going to be good at that, then your trade-offs become easier. And it's the same. When you're very honest about what you don't know, what you aren't good at, you can be very clear about how you're going to go get it. We're not going to pretend that we had vast experience in this domain or that domain. We're honest. We're, good Lord, we got to do better here. We got to find some people, and we've got to put in a multi-year effort to build relationships with academics, with researchers, with et cetera, in order to be strong there.
So I know there are questions coming in. I want to ask one related to kind of the path to commercialization. One of the things that Andrew's painted, obviously here today, a very compelling technical story about what we're building, and but one of the things that I think from the market perspective and the use cases that is super interesting is really this notion that heretofore AI has been kind of a king's game. You basically needed to have the data assets, you needed to have the computing power, you needed to have all those resources. And one of the things that I think has been driving you all along is how do we enable just this massive wave of pent-up demand in the mid-market, and for the crazy researchers and the third graders and the kindergartners who don't have Google's TPU pods?
Right. We are not fans of Goliath. Right. We root for David. That's why we sort of choose this path. And we choose to root for Davids, for the underdogs, in every sector, not just in our choices to go after big companies with tens of thousands of engineers and hundreds of billions in market cap. We see that we take great pride in the fact that our technology can be a leveler, and that we can provide for, a few $1 million and 20 kilowatts what others take 40 million and half a megawatt to provide. That we can fit into standard colo, and the other guys' solutions have dedicated buildings for their solutions. And so that sort of drives us. It's part of our DNA that we would think of ourselves as failures if we made Google better. Right? That's not helpful. We want to make researchers around the world better. We want to make it so that you can take a photo of a skin lesion with a cheap phone in India and get a very reasonable diagnosis in the cloud for free. That's what we want to do. So that at every stage we're seeking ways to make the little person, to empower the little person.
Andrew's dad, by the way, teaches evolutionary biology, so you can see some of the the references here. I'm sure you look at everything competition as well through a Darwinian lens.
Well, Mom was a psychologist, so we had nature and nurture. We had
exactly.
both.
Soft and hard. So a question that came through, just some folks are very curious about when you're planning to launch. I didn't actually see that question, but can you tell folks a little bit more about kind of the status and the commercial traction?
Sure. We'll be announcing the full system at the Supercompute show in November. And so we are a system company. It comes in a 15 rack unit enclosure. We'll be announcing it then. We'll be announcing customers. We will be announcing performance. A whole set of data will come out at that time. We tried to avoid the marketing fury where first you announced that you raised money, and then you announced that you rented a building, and then you announced that you hired a real estate agent to rent another building. We thought that was ridiculous. And so we just stayed quiet. And one of the advantages of being a little older and being in the industry for a little while is we knew top-tier venture capitalists. We knew the top customers in the world. We built relationships with the leading labs in the world and the leading scientists. And so the useless marketing noise was something we could avoid. So we waited till we had something. And very shortly after that, we announced the chip 2 or 3 weeks ago. And within 90 days, we will... I brought it up here. You can come and see it. This is a big chip. This sad little thing is an NVIDIA GPU. Right. My wife jokes that I travel everywhere with this now. And it's sort of true. So we will have all of that. I think we put a little news out about a partnership next week, but I think the next few months will be filled with real meancemeaningful information about our company and about our progress.
And for folks who are curious to learn more about the company and maybe should be working with Cerebras, what are the sort of the most critical areas of development?
So having only been at a big company when they acquired my little companies, I recruit in a different way. I don't have boxes I'm trying to fill. I'm looking for extraordinary athletes. And so if you are extremely talented, if you love your domain and are a student of your domain, we're happy to talk. I'm just Andrew at Cerebras.net. I spend about a third of my time recruiting, a third of my time with customers, and a third of my time answering board questions. No, a third of my time managing the leadership team. We got a question over here. So, sure. Repeat the question. Andrew, you didn't just try and solve an open 70-year problem in the chip world, but you took upon yourself a vast number of other problems that carry along with it, like how you build software for a 400,000 core machine. Well, we know a couple things. We know that people hate programming massive parallel machines. And that the only people that are very good at it are in supercomputer shops around the world. And so that was something we had to avoid like the plague. And so the technical challenge at the highest level was, how do you take something that's basically Python, a Python library like PyTorch or TensorFlow, written by someone who has no real understanding of locality, how memory works, et cetera, extract all the parallelism out of it, present it to a massively parallel array so that it can be operated on in a blisteringly fast manner. That was the problem. To do that, we looked at a bunch of existing problems. Synthesis in an FPGA has some of the same characteristics, and there's people with PhDs in optimization problems that look like place and route problems or floor planning problems. We borrowed, we invented. We looked at many different approaches to try and wring all the performance that the underlying hardware was going to deliver out of the software as written. And as a system company, we're about 200 engineers right now, and about 130 of them are software engineers.
And close to 100 are PhDs, and from now 35 countries?
We do. We put a map up on the wall because I was tired of the immigration debate. So everybody remembered where we're from. We're from 36 countries.
36, right.
And from all over the world. And what is good about Silicon Valley is the best and the brightest come here. From all over the world. We got to do our best not to get in the way of that. They come to our great schools. We then make it hard to get jobs with ridiculous immigration hurdles. And when you go out to build great companies, the only thing you care about, not race, not religion, not what God you worship, not here in the Valley, not sexual orientation. We only care about, can you write code? How good an engineer are you? Because we can't afford to pass. We can't afford to pass people who are stories. They're just too rare.
We probably have time for one more question. Yeah.
I'm a long-time semiconductor technologist, not an investor, but the fundamental problem of yielding this thing just is too mind-boggling, and it's not about innovation. This industry has been forever trying to make bigger chips yield. So, you can't innovate around some of the fundamental problems of yielding something that big.
Sure, I can. I think we innovated around the fact that the reticle has a limit of about 840 square millimeters. By inventing techniques that allowed us to pattern and allowed us to communicate across the scribe line. We realized that this was a small core workload, and if I built a perfect array of 407,000 cores, what I could do is I could use some of them as redundant and use the exact same techniques that they've been using in memory, where they hold aside bit cells and shift rows. So I don't have to get a perfect wafer. I withstand the flaws that TSMC delivers. and still yield 100%. So it was a combination of understanding what the workload demanded of the core and having enough understanding of the physical realities and the physical techniques that were available to use redundancy to solve the problem of yield. And if you have a large number of identical cores, the penalty you pay for redundancy is very small. We drop down about 1.5% more cores than we use. So that's a tiny penalty to pay to yield the largest chip ever made. So I think we are pathological rule not followers. That's probably not good English. We look at rules and existing limitations as challenges to overcome. And when we sat down with lithography team at Fab 14 at TSMC and explained what we wanted them to do, they had big smiles on their face. We've been waiting for this project. We're all in. And in the last 3 years, the only chip they've added to their museum in Taipei is our chip. Thank you, guys.
Not far from the Computer History Museum. I hope it'll be there someday. Andrew, thank you so much.
Thank you so much, guys.